In this example, we're going to find the radius and interval of convergence for the following series. Remember, when you have a power series is of the form sigma as n goes from 0 to infinity of c sub n x to the nth power. Or if we have a power series that is centered at A, then we have sigma as n goes from 0 to infinity, c sub n, x minus a to the nth power. So for this bottom power series, we say it is centered at A. And then for the first one, we say that that power series is centered at 0. So we need the power series to be either centered at 0 or at A so that we can then find the radius of convergence. And remember, we find the radius of convergence when we have something in the form of x minus a in absolute value less than r. So r is the radius of convergence. And then when you solve that absolute value inequality, you get x minus a is less than r, but greater than negative r. And then we say we have a minus r, x, and a plus r. So you'll have something in the form of a minus r, a plus r, and this here will be the beginning of your interval of convergence. So let me just call it for now interval of convergence. But remember, when you're talking about the interval of convergence, you must check the endpoints. So if we check the endpoints, you could have an interval of convergence as you see it up here, a minus r and a plus r, where the endpoints are excluded. Or you could have something in the form of a minus r, a plus r, or a minus r, a plus r, where one of the endpoints is included. And that is the series will converge at the endpoint. Or we can have something like this, where the power series, your series, will converge at both of the endpoints. This is why it's important for us to check the endpoints. Okay. So let's go back to the original problem. What we're going to do is we are going to ask ourselves, for what values of x does this series converge? So in order for us to find the radius and the interval of convergence, we're going to use, in this case, the ratio test and see for what values of x does this series converge. So the ratio test, we're going to say the limit as n is approaching infinity of the absolute value of the square root of n plus 1 times x plus 6 to the n plus 1 power over 8 to the n plus 1. And then times, remember for your ratio test, we're going to do the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So division by a fraction becomes that multiplication of the reciprocal. So we are going to have a to the n over the square root of n times x plus 6 to the nth power. And then we can begin to simplify a couple of things. We're going to have the limit as n approaches infinity of, we're going to simplify 8 to the nth power with 8 to the nth power. Remember, 8 to the n plus 1 is 8 to the nth times 8. So all that I'm doing is I'm simplifying 8 to the nth power, both from the numerator and the denominator. So I'm going to just simplify that n there, but it cancels an 8 to the nth. Same thing for x plus 6 to the nth and x plus 6 to the nth. So we're going to be left with x plus 6 over 8 times the square root of n plus 1 over the square root of n. The x plus 6 over 8, that's considered a constant because we're taking the limit as n is approaching infinity. And because x is not n, we're going to take that out and say this is x plus 6 in absolute value over 8 times the limit as n approaches infinity of the square root of n plus 1 over the square root of n. And what I'm going to do is I'm going to multiply both the numerator and the denominator by 1 over radical n. When we multiply both numerator and denominator by that, let me write this down. Then this is going to give us the square root of n over n plus 1 over n over the square root of n over n. And if we do the square root of that, then this is 1, this is 1, and as n approaches infinity, 1 over n will go to 0. So then the limit as n approaches infinity is equal to 1. Now remember, we're working with a ratio test, and the ratio test says that the series will converge. The series will converge whenever that entire answer is less than 1. So if we are looking for the absolute value of x plus 6 over 8 less than 1, then we're going to solve for the absolute value, and we get x plus 6 is less than 8. Now remember up here, we talked about x minus a in absolute value less than r. And when we talked about that stuff, we said that r was that radius of convergence. And then we said the center was at a. So with this information, we can say that the center a is equal to negative 6 and r is equal to 8. And just to make sure that you see it, we need to have it in the form of x minus a. So x minus a negative 6 less than 8. Okay? So your a is negative 6. All right. To find the interval of convergence, we need to solve that absolute value inequality. And to solve the absolute value inequality, you get an x plus 6 less than 8 but greater than negative 8. And then we get x is less than 2 but greater than negative 14. So we're almost there. You have an interval of convergence But remember we talked about that? We must now check the endpoints. So what happens if x is equal to negative 14? So what happens if x is equal to negative 14? When you plug it back into your original problem, you have sigma as n goes from 1 to infinity, the square root of n over 8 to the n. And then when you plug in negative 14 for your x, you get a negative 8 to the nth power. We can simplify that and say this is sigma as n goes from 1 to infinity of negative 1 to the nth power times the square root of n. And let's look at that. Let's look at the limit as n approaches infinity of the absolute value of negative 1 to the n radical n. And that is going towards infinity. So as your n gets bigger and bigger and bigger, your series will be alternating, but also, let me put it here, getting bigger and bigger. So we can say that because this limit is equal to infinity and you have an alternating series, we can say that the series n equal, as n goes from 1 to infinity, of radical n over 8 to the n times negative 8 to the n is divergent by the test for divergence. So the idea here is that the limit as n is approaching infinity of negative 1 to the n radical n does not exist. Now let's plug in 2 into our problem. So we're going to have sigma as n goes from 1 to infinity. We have the square root of n over 8 to the n. And then when you plug in 2 into your original problem, then this gives you 2 plus 6, which is 8. So times 8 to the n. And this is going to be sigma as n goes from 1 to infinity of the square root of n. And again, we can say that the limit as n approaches infinity of the square root of n is going to be equal to infinity and therefore divergent by the test for divergence. So we can say obviously it's not equal to 0. So therefore this series is divergent by the test for divergence. You can make an argument too that it diverges by the p-test. I won't talk about it, but you can make that argument. Now here we're not done. Well, I guess I could talk about it. So this you can write it down as n from 1 to infinity of 1 over n to the negative 1/2. And because p is less than 1, then we can say that series is divergent by the p-series test. All right, so remember, the problem was asking for the radius of convergence, and we found that earlier. We found the radius of convergence. So the radius of convergence R is equal to A, and the interval of convergence, I'm sorry about the noise in the background. Interval of convergence is from negative 14 to 2. And this here is what the problem was asking for.